Oscillators are electronic circuits. They are critical parts, important parts that go into the design of electrical communication transmitters and receivers. They have several other applications too. They provide a stable fixed frequency voltage waveform. The frequency of the waveform provided by the oscillator, it depends upon various components, their values and parameters of the active element that goes into the design of oscillator. Problems set around the connecting relations between frequency and component and parameter values of the oscillator circuit and the solutions of the problems. Going through them help us a lot to understand the functioning, the physics of the oscillators. They help us a lot in the design of oscillator circuits. Analog circuits, oscillators problems, series on semiconductor devices and circuits, lecture number 10.14. Oscillators are electronic circuits. They are capable of generating a stable periodic voltage waveform. They are, along with amplifier circuits, important parts in the design of transmitters and receivers of communication systems. In the present session, we consider various problems set around electronic oscillators. Now we move further to begin the core session. We start the session with a problem. Example 1. In an RC phase shift oscillator, R is 200K, C is 100 picofarads. Find frequency of oscillation. Also find frequency of oscillation when A. R is 500 kilo ohms and B. C is 10 picofarads. Solution. The given oscillator is RC phase shift oscillator. For this, frequency is 1 by 2 pi RC root 6. R is given, C is given. Substituting the given values of R and C, one can determine F. It turns out to be 3.248 kHz. When R is changed to 500 kilo ohms, same formula, using same formula, one can find frequency as 1.299 kHz. When C is changed to 10 picofarads, frequency of operation can be determined using the same formula, F equal to 1 by 2 pi RC root 6. It turns out to be 32.48 kHz. Another problem, example 2. In a FET RC phase shift oscillator, R is 200 kilo ohms. Find the range of capacitance needed to vary the frequency of oscillation from 35 kHz to 50 kHz. Solution. Frequency and capacitance of RC phase shift oscillator. They are related through F equal to 1 over 2 pi RC root 6. From this, C equal to 1 by 2 pi RF root 6. Now, capacitance at frequencies 35 kHz, 50 kHz. They can be found as 9.28 picofarads, 6.50 picofarad. Hence, required capacitance variation is 9.28 picofarad to 6.50 picofarad. It means tuning range of 35 kilohertz to 50 kilohertz requires a capacitance variation of 9.28 picofarads to 6.50 picofarad. Another problem, example 3. In an RC phase shift oscillator, RC is given as 2.5K, R is 10K, C is 0.05 microfarad. Determine frequency of oscillation and minimum required current gain. Here, the phase shift oscillator uses BJT, RC. Presence of RC indicates that it is BJT oscillator. Solution. Here, K is RC by R. RC is given, R is given, so it turns out to be 0.25. The formula, the relation from frequency is 1 by 2 pi RC square root of 6 plus 4K. R is available, C is available, K is known, so frequency of oscillation can be determined without any difficulty. In this case, it turns out to be 120.31 Hz. The condition on the gain for oscillations is HFE should be more than 4K plus 23 plus 29 by K. So substituting the available values of K, one can find HFE more than 140. So small signal short circuit gain must be more than 140 to sustain oscillations. Another problem, example 4. Find C, capacitance HFE, current gain of a transistor to provide a frequency of a 50 kHz from a RC phase shift oscillator. Given R1 is 22 kilo ohm, R2 is 68 kilo ohm, RC is 20 kilo ohm, R is 6.8 kilo ohm, HIE is 2 kilo ohm. HFE is given, RC is given. Therefore, the RC phase shift oscillator in the problem must be a BJT 1. For BJT RC phase shift oscillator, frequency is 1 by 2 pi RC square root of 6 plus 4K. From this, C can be found as 1 by 2 pi RF naught square root of 6 plus 4K. K can be determined. K is RC by R. RC is given, R is given. Substituting the given values, K can be found as 2.94. Now, C is 1 by 2 pi R. R is given. F naught is given, 50 kilohertz. K is available, determined. So C can be found as 0.111 nanofarads. HFE should satisfy the relation. It should be more than 4K plus 23 plus 29 by K. K value is available. Substituting that value in this relation, HFE can be found as more than 44.62. So small signal short circuit current gain must be more than 44.62 to sustain oscillations for this oscillator. Example 5, another problem. In a Hartley oscillator, L2 is 0.2 millihenry, C is 0.004 microfarad. If the frequency of the oscillator is 150 kHz, neglecting mutual inductance, find the values of L1. Also find its values when L2 is 0.4 millihenry, C is 0.004 microfarad, and frequency is 120 kHz. Solution. Frequency of a Hartley oscillator is given by this formula. F equal to 1 by 2 pi square root of L1 plus L2 C. From this, L1 becomes equal to 1 by 2 pi whole square F square C minus L2. So F is given, C is given, L2 is given. Substituting the given values, L1 can be found. In the present case, it turns out to be 0.08 millihenries. By working out in a similar manner, L1 can be found as 0.04 millihenry when L2 is 0.4 millihenry. C is 0.004 microfarads and frequency is 120 kilohertz. Another problem, example 6. In a Hartley oscillator, the inductances are L1 equal to 40 microhenry, L2 is 15 microhenry. Find its frequency and feedback factor when the tuned circuit capacitance is 500 picofarad. Solution. We have seen in the previous problem, similarly here also, frequency of Hartley oscillator is 1 by 2 pi square root of L1 plus L2 C. Substituting the given values, one can find frequency as 0.96 megahertz. The feedback factor beta is L1 by L2. L1 is available, L2 is available, both are given. So the ratio can be determined. It is 2.66. Another problem, example 7. In a Hartley oscillator, inductances are L1 equal to 2 millihenry, L2 equal to 20 microhenry. Frequency is to be changed from 1 megahertz to 2 megahertz. Find range over which capacitance is to be varied. The frequency and capacitance in the Hartley oscillator, these two are related through F equal to 1 by 2 pi root L1 plus L2 C. Notice this L1 plus L2 C is under square root. From this, C can be found as equal to 1 by 2 pi whole square F square L1 plus L2. To give 1 megahertz frequency, the capacitance C should be. So F is 1 megahertz, L1 and L2. They are given as 2 millihenry, 10 microhenry. Substituting those values, C can be found as 12.53 picofarad. In the same way, to give 2 megahertz frequency, the capacitance can be found as 3.13 picofarad. Therefore, capacitance requires to be changed from 12.53 picofarad to 3.13 picofarad. So a variation from 12.53 picofarad to 3.13 picofarad is required to have the desired frequency variation. Another problem, example 8. A Colpitt's oscillator is working at 500 kHz with the C1 equal to C2. Find frequency of operation when its values of capacitances are doubled and halved. Solution. Frequency of operation of Colpitt's is 1 over 2 pi root LC equivalent, where C equivalent is C1 C2 by C1 plus C2. When capacitances are same, C1 equal to C2, let us call this capacitances as a C, simply C. C1 equal to C2 equal to C. So C equivalent becomes C by, hence frequency of operation becomes 1 by root pi root LC. Substituting the given values, one can find frequency as 500 kilohertz. When capacitances are doubled, then frequency of operation, it becomes 1 by root 2 pi square root of 2 LC. It is equal to F by root 2, becomes equal to 353.6 kilohertz. Here F is 500 kilohertz, which we calculated just now. When capacitances are halved, the frequency of operation becomes root 2 F. F is 500 kilohertz. It becomes 707 kilohertz. Notice halving the capacitances increases the frequency of operation by root 2 times, that is 1.414 times. Another problem, example 9. A Colpitt's oscillator is designed with C1 equal to 100 picofarads, C2 is 8 nanofarads. The inductance is variable. Find the range of inductance value if the frequency of oscillation is to vary from 1 megahertz and 2 megahertz. Work out the problem when C1 is 200 picofarads. Given oscillator is a Colpitt's. Now solution. With the capacitances 200 picofarads and 8 nanofarads, C equivalent becomes 98.76 picofarads. Frequency for Colpitt's is F is equal to 1 by 2 pi square root of L C equivalent. Expression for inductance L becomes equal to 1 by 4 pi square F square C equivalent. For frequency 1 megahertz, the inductance becomes, when F is 1 megahertz, what is inductance? It can be determined easily. It turns out to be 0.256 millihenry. For frequency 2 megahertz, inductance can be determined. It turns out to be 0.065 millihenry. With the capacitance C1 equal to 200 picofarad, it can be found C equivalent equal to 195.12 picofarad and inductance 0.1 millihenry, 0.03 millihenries. Another problem, example 10. In a Weinbridge oscillator, find value of capacitance when R is 100K and frequency is 10K. Find its value when R is 500K and frequency is 100K. Solution. For Weinbridge oscillator, capacitance can be obtained from frequency operation as F naught is 1 by 2 pi RC, so C is 1 by 2 pi R F naught. Substituting the given value R and F naught, C can be determined. It turns out to be 159 picofarad. When R is 500 kilo ohm and frequency is 100 kilohertz, capacitance can be determined in the same way. It turns out to be 3.18 picofarads. Another problem, example 11. A crystal resonates at 500 kilohertz. Its equivalent inductance is 4.2 Henry. Equivalent capacitance is 0.03 picofarad. Its equivalent resistance is 500 ohms. Find its Q factor. Also find Q factor when a resonating frequency is 700 kilohertz, inductance is 5 henries, capacitance is 0.10 picofarad and resistance is 1 kilo ohm. Now, solution. Substituting the given value, the Q factor can be found from the expression Q equal to omega L by R. Omega is 2 pi F. When F is available, L is available, R values are available, then Q can be determined. For the present case, it turns out to be 26,389. Now, we consider one after another A, B, C, D. A. In this case, the resonating frequency is 700 kilohertz. Therefore, Q becomes 36.945. In B, inductance is 5 Henry. So Q is 34,416. In case of C, capacitance is 0.10 picofarad. For this, Q can be obtained. It turns out to be 26,376. In D, resistance is 1 kilo ohm. So Q for this case is 13,194. Another problem, example 12. A crystal has the following parameter. L 0.6 Henry, CS 0.05 picofarad, CP is 1 picofarad, and R is 6 kilo ohm. Find series and parallel resonant frequencies and Q factor of the crystal. Solution. The series resonant frequency of the crystal is given by this form. Fs is equal to 1 by 2 pi root L C prime. By noting C prime is Cs, the series resonant frequency can be obtained from the given values of L and C prime as 918.9 kilohertz. Q factor of the crystal at this frequency is omega s L by R, 2 pi Fs L by R. Substituting the given values, one can determine it. It turns out to be 577. Another problem, example 12. No, this is continuation of the previous problem. Parallel resonant frequency of the crystal is Fp is square root of C prime plus C, whole thing divided by 2 pi square root of L C prime C. Using the given values, one can find Fp as 941.6 kilohertz. The Q factor of the crystal at this frequency is omega p L by R. Substituting the given values, it comes out to be 591.62. With this, we come to the end of the session. Before closing down, let me mention solution of these problems, especially in the present session problems. Intelligence is not required. What is necessary to solve these problems is expressions for frequencies of the oscillators. Ability to remember the expression for frequencies of the oscillators. This is required. Hope this session is useful to you. Meet again in another session very soon with a new topic.